Medical physics for you.
Hello everyone. Welcome to another lecture. Today we are going to start our discussion about the measurement of ionizing radiation. Today we will see what are the principles of ionizing radiation measurement. What is the exposure? Electronic equilibrium. First, let's ask ourselves, why do we need to measure the ionizing radiation? And what is the principle of ionizing radiation measurement? To answer the first question, let's assume that there is a radiation source beside you right now. Will you be able to recognize that? The answer is, no. The problem is that the radiation is intangible and does not have color or odor. So, as humans, we cannot detect if there is a radiation source around us or not, and we need to have some kind of assistance to be able to detect it. This assistance is in form of instrument. To answer the second question, that instrument should not be able only to detect the radiation, but also has some relationship with the amount of radiation that it detects. In other words, the effect that is going to be measured using that instrument should be proportional to the amount of received radiation. Historically, detecting radiation was based on some chemical and biological effects that it can generate. For example, the amount of radiation absorbed may have an impact on photographic emulsions, altering the color of certain chemical compounds. Radiation also can cause skin reddening in humans. These effects, however, could only provide an approximate estimate of radiation exposure because they were not well understood at the time. The skin erythema dose was used at some point to quantitate the radiation amount. But the skin erythema dose does not depend only on the amount of incident radiation, but depends on many other factors like the type of skin, quality of radiation, extent of skin exposed, dose fractionation, and so on. So these methods of radiation measurements were not ideal and more reliable methods were needed. With the increase using of radiation, there was a higher demand for more reliable units for radiation measurements. One of the first units for radiation measurements is the Roentgen. Roentgen is the unit for radiation exposure. Exposure is the amount of charges produced in air by photons. X is the exposure, dq is the total charge of the ions of one sign produced in air when all the produced electrons are liberated by the incident photons in air of mass dm are completely stopped in air. So, for exposure, the conditions are, produced by photon in air and the produced electrons are fully stopped in air. In 1928 the International Commission on Radiation Units and Measurements, ICRU, adopted the Roentgen as the unit of measuring radiation exposure. 1 Roentgen equal to 1 electrostatic unit per cubic centimeter air at standard temperature and pressure. By this definition, 1 electrostatic unit equals 3.333 by 10 power to minus 10 coulomb, and 1 cubic centimeter air equals 1.293 by 10 to power minus 6 kilograms. So, 1 Roentgen equals 3.333 by 10 to power minus 10 divided by 1.293 by 10 to power minus 6 equals 2.58 by 10 to power minus 4 coulomb per kilogram. That means the amount of charges produced when 1 Roentgen fall on 1 kilogram of air is 2.58 by 10 to power minus 4 coulomb. To understand exposure, let's imagine that there is air volume within a definite area represented by the dotted lines. This volume is exposed to X-ray beam. As we have discussed in the interaction of photon with matter lecture, as a result of these interactions, electrons will be released either due to photoelectric effect, Compton effect, or pair production. These released electrons will produce ionization along their tracks. Now imagine two plates with applied voltage are surrounding the air volume. The produced ions, electron and the positive remaining of the atoms, will be attracted to the plates. The electrons, negative charged particles, will be attracted to the positive charged plate. while the positive ions will be attracted to the negative charged plate. This ion's movement will induce current that can be measured by an electrometer. Some of the ions produced in the shaded volume can escape that area and deposit their energies outside the collection region. In this case, these ions released due to incident photon won't be collected by the plates, in other words, cannot be or won't be measured. On the other hand, some of the ions produced outside the shaded volume can enter that volume and deposit their energy within the collection region, i.e. measured. If the amount of escaped ions equal to the amount of the ions entered the region, this is known as electronic equilibrium. Only in this case the definitions of Roentgen is satisfied. Electronic equilibrium is a very important principle in radiation measurements, as we will see in the next lectures. Now, it is time for some questions. Question 1. What is Roentgen? Roentgen is the unit of the radiation exposure measurement, and it is the amount of radiation that can produce 2.58 by 10 to power minus 4 coulomb when it falls on 1 kilogram of air at standard temperature and pressure. Question 2. What does the electronic equilibrium condition mean? Electronic equilibrium condition means the condition where the amount of ions escape from the measurement's volume equal to the amount of ions enter it. In the electronic equilibrium condition, all the secondary electrons produced are fully absorbed in the measurement volume. That is all for today's lecture. Thank you.